Hello students, welcome to EPG Pathshala. I am Professor P03 from Jammu. Today we are going to discuss about a module elements of crystallography under paper crystallography and crystal growth. So students, let us see what we are going to study in this module. Origin of crystallography, what do we mean by a crystal, definition of symmetry, various symmetry elements. Let us talk about the origin. The science of crystallography started with the study of the external form and habit of crystals which grow in nature. The naturally occurring crystals, bounded by multiple faces, have attracted the fascination of man since long. Figure 1.1 is a schematic illustration of naturally occurring quartz crystal with multiple flat faces. The morphology, that is the external regular arrangement of crystal faces, was taken as suggestive of internal regular arrangement of atoms. Nicholas Steno in 1969 established a law of interfacial angles. He observed that the interfacial angles of a crystalline solid are always the same irrespective of how and where they grew. The external form of crystals manifests internal regular arrangement of atoms that compose them. Crystals may be of several different shapes and sizes, say for example, small cubes, long thin needles, small platelets. For any given chemical composition, they are all built up out of atoms, molecules, or ions, which are arranged regularly in the crystal in the same way, irrespective of the external shape of the crystal. This is illustrated through schematic diagram of figure 1.2, considering for the sake of simplicity a two-dimensional example. Here we take the example of 4 sets of solid circles, each set being of different shape, but each of them has the solid circle arranged in the same pattern within the figure. Each figure consists of several squares with solid circle at their centers, which are located side by side in the same order, and one of these solid circles is drawn in each of the cases shown in figure 1.2 A and B. The differences between the 4 figures are on account of the fact that the boundaries have been drawn in different ways. One could cut out 2 of these shapes from a large area containing solid circles arranged in this same regular order. It is not the shape and size of a crystal that holds so much importance. It is, however, an important fact that the angles between the habit faces are always the same on account of a regularity in the arrangement of atoms of which the crystal is composed. The schematic diagrams of figure 1.2 A and B illustrate the fact that the crystals of any chemical composition may differ very widely in shape and size. Their interfacial angles are the same for various different specimens of the chemical composition. A crystal may therefore be defined as a solid with plain naturally occurring faces and in which the composing atoms, ions, or molecules are regularly arranged. The outward orderliness of crystal is only a manifestation of the internal orderly arrangement of the atoms or molecules of which the crystal is composed. Generally speaking, the term solid is applied to rigid elastic substances which exhibit elastic behavior when they are subjected to hydrostatic forces and also under tensile, or shear stresses. Materials regarded as solids may generally be divided into two categories: amorphous and crystalline. In amorphous substances, the atoms or molecules may be bound very strongly to one another, but there is no geometrical regularity or periodicity in the arrangement of atoms composing these substances. Such substances are usually viscoelastic and may be regarded as supercooled liquids. Figure 1.3ab are schematic representation in two dimensions showing the difference in atomic arrangement between a crystalline and an amorphous material. In figure 1.3a, one finds atoms of the same type at regular positions throughout. Say, for example, atoms shown as solid circles are situated at regular sites with same interatomic distance throughout. The hollow circles, which may refer to atoms of different type, are also regularly arranged. It's not so in the case of figure 1.3b. Be it atoms of one type, say solid circles, or atoms of different type, say hollow circles, they are randomly arranged. We call it an amorphous state. Glass is an example of amorphous material, whereas quartz shown is an example of crystalline solid. The term crystalline state is used to describe substances which apparently may not look like crystals, but which nevertheless possess an orderly internal arrangement of atoms or molecules. The best example is those of metals, which apparently may not appear to be crystals on account of the fact that they are found in irregular lumps, but they certainly belong to the crystalline state because the atoms in a given metal are arranged regularly. For example, one may offer the case of aluminium, which is made up of a very large number of the small cubes, as shown in figure 1.4, all packed together so as to fill space completely. The solid circles in the figure are the aluminium ions. It has a face-centered cubic structure in which the unit cells or building blocks represented by, say, L, M, N, O, P, Q, R, S are cubes with an atom at each of the corners and an atom at the center of each of the 6 faces of the cube. Several metals, for example, gold, cobalt, copper, silver, and several others, exhibit this structure. It only points out the fact that those subsolid substances may not necessarily look like crystals, yet they, in reality, are actually crystalline. Guggenheim Mini in 1688 observed that some solids exhibit the property of cleavage under an application of small stress. Calcite crystals exhibit easy fracture along certain crystallographic planes, each of 2 surfaces being smooth and plane. Mica, diamond, and several other crystals show the property of easy fracture along certain crystallographic planes. The crystallographic plane along which cleavage takes place is a characteristic property of the crystal. It was Guggenheim Mini who studied the constancy of cleavage direction in a given crystalline solid. Abbe Hoy carried the study further in 1784. Study on cleavage of solids led him to conclude that the smallest unit of which the crystal is built up was independent of the external shape, that is, the morphology. His work laid the foundation of crystallography and, as such, is credited with the title of Father of Crystallography. It is now known and established beyond doubt that a certain fundamental building block, each block may be in the form of a group of atoms, ions, or molecules, etc., which repeats at regular intervals, exhibiting a periodicity in all the three dimensions in a crystalline solid. The fundamental building block is termed as unit cell of the crystal. Basic understanding of symmetry is that if a geometrical figure is folded along a line so that the two halves match exactly, then the figure is said to have a line of symmetry, as shown in figure 1.5. Figure 1.5a shows a line of symmetry, and figure 1.5b shows a rectangle having two lines of symmetry. Figure 1.5c shows a square having four lines of symmetry. Figure 1.5d shows an equilateral triangle having three lines of symmetry. Figure 1.5e shows a hexagonal figure having multiple lines of symmetry. Let us explain the figure 1.5 C, D, and E further. Figure 1.5c shows a square having four lines of symmetry. It shows a square having four lines of symmetry AC, BD, GH, and EF. As one can see, triangle ABC is the mirror image of triangle ACD. Similarly, BCD is the mirror image of BAD, and likewise HGCD is the mirror image of ABGH. FBCE is the mirror image of AFED, and so on. Regarding 1.5D, it shows an equilateral triangle having three lines of symmetry, say AE, BF, and CD. AB is the mirror image of AEC. Similarly, BCF is the mirror image of BAF, whereas BCD is the mirror image of ADC. So we can say that an equilateral triangle has three lines of symmetry. Figure 1.5a shows a hexagonal figure having multiple lines of symmetry. It is a regular hexagonal figure with multiple lines of symmetry. For example, if we look at the figure and take GJ as a line, GBCDJ is the mirror image of GAFEJ. Similarly, let us take the line FC, which divides the hexagon into two parts, which are the mirror images of one another. CDEF being the mirror image of CBAF, and so on. So this way we can say that regular hexagonal figure has multiple lines of symmetry. Any regular figure exhibits one or the other type of symmetry. Element of symmetry refers to an operation which, when performed, may bring about congruency of the figure. Crystals show external symmetry, which suggests that most of them exhibit geometric symmetry. The symmetry may be about a point, line, or a plane, or any of these combinations. Symmetry is characteristic of any regular geometrical figure. This is what applies to solid crystalline materials which exhibit a regular arrangement of atoms, ions, or molecules that compose them. Let us consider fundamental forms of symmetry operation that can be executed to periodically repeat the basic building block of atoms, ions, or molecules, also known as motif in space. Translational symmetry. To illustrate translational symmetry, we may consider numerical figure 7 here for the sake of convenience and understanding as shown in figure number 1.6. If we move numerical figure 7 by a distance, say A, to the right, the same numerical figure 7 would be located at point P. This is called translational symmetry operation and obviously can be repeated any number of times. There can also be translational symmetry operations in other directions, up the page, down the page, to the right or left of the page, and there can be compound translations such as 2A to the right and 1A up the page taking O to R. The situation is very similar to how chess players move knights while playing the game of chess. Rotational symmetry. One can achieve congruency of a figure by rotation about an axis through a particular angle, say theta, as for example in the case of numerical figure 7 shown in figure 1.7. If the congruency of the numerical figure about an axis is achieved by a rotation of 2 pi by n, where n can be 1, 2, 3, 4, and 6, we can say it has axis of symmetry. For n equal to 1, 2, 3, 4, and 6, congruency is achieved by a rotation about an axis through 360 degrees, which is possible in all cases: 180 degrees, 120 degrees, 90 degrees, and 60 degrees respectively. If n is equal to 2, the axis is named as dyad. If n is 3, the axis is triad. If n is 4, the axis is tetrad. If n is equal to 6, the axis is hexad. Reflection symmetry. One can achieve congruency of a figure by reflection from a line in the two-dimensional case or from a plane as shown in figure 1.8ab. If we keep a mirror along BD, BCD is the mirror image of ABD in figure B, or the top numerical figure 7 is the mirror image of the lower numerical figure 7 in figure A. Figure 1.9 is the illustration of symmetry by inversion through a point O. As one can see, symmetry about a point is possible by inversion through the point as is shown in this particular figure number 1.9 for the numerical figure 7. Mixture of symmetry operations. Symmetry elements can be of more complex type. To understand this, consider a situation shown in a schematic diagram of figure 1.10. In figure A, we have a translational symmetry as explained above. Repetition of numerical figure 7 occurs if we move it by a distance, say A. However, the situation is different in case of an arrangement as is shown in figure B. Unlike the arrangement of figure A, one does not find a repetition of a numerical figure 7 occurring after every movement by a distance A. One can achieve a repetition of numerical figure 7 by moving it at distance A, say digit 7 at M, to the right, but also to be reflected in the line XY so as to make it appear to be the same as before. On performing this compound operation, the numerical figure 7 at M moves to position N and turns it upside down. In the same way, it moves O to position P, followed by reflection in the line XY, moves it to Q, turning it upside down at the same time. It is a composite operation which is known as glide reflection operation of symmetry. One of the many examples of solids which exhibit this kind of symmetry element is diamond that possesses glide planes of symmetry. The glide planes of symmetry are a mixture of a translation operation and a reflection operation. Figure 1.11 A and B is another schematic representation which shows a glide in which reflection is combined with translation parallel to the plane of mirror plane. Symmetry operations, which are a mixture of translation operation and rotation operation, are known as screw axis of symmetry. The screw rotation operation is a combination of a rotation operation and translation operation in the direction of the screw axis. The structure assumed by diamond has a four-fold screw rotation axis of symmetry. So, students, let us summarize what we have learned in this module. The general form of crystals manifests internal regular arrangement of atoms that compose them. Crystals may be of several shapes and sizes, but for any given chemical composition, they are all built up out of atoms. Molecules or ions, which are arranged irregularly in the crystal in the same way, irrespective of the external shape of the crystal. Guglielmini in 1688 observed that some solids exhibit the property of cleavage under an application of small stress. Mica, diamond, and several other crystals show the property of easy fracture along certain crystallographic planes. The crystallographic plane along which cleavage takes place is a characteristic property of the crystal. It was Guglielmini who studied the constancy of cleavage direction in a given crystalline solid. Abbe Hoy carried the study further in 1784. A regular geometrical figure exhibits some symmetry elements which may be about a point, a line, or a plane. An operation which may bring about congruency of a geometrical figure can be termed as a symmetry operation. Various symmetry elements exhibited by a regular geometrical figure are described. Thank you.